So in this video, we're going to conceptually develop the washer method, which is just an extension of the disk method for finding volumes of revolution. And here's the idea. Suppose that we have a region bounded above, so I'm going to call this region R, bounded above by f of x and bounded below by g of x. So we're looking at the region between the two bounding curves, and we want to take that region and only rotate it around an axis, let's say the x-axis, and I want the volume of that region revolved through three-dimensional space. Well, if we revolve this region through three-dimensional space about the x-axis, so here's the region right here being revolved about the x-axis, what I want to recognize is that the interior is going to be empty. And the washer method is just a method for applying the disk method for finding volumes of revolution to these cases where we have bounded regions where the region interior is going to be empty. It plays off the two-dimensional analog where if you have a washer, so this is all solid, if you have a washer and you want the area, so I'm not talking about volume right now, but if you want the area of the outer part of the washer, you would use the larger radius to find the area of the whole circle, and then on the little circle on the inside there's going to be a smaller radius, call it little r. You would calculate the area of the little little circle and you would subtract it off. So what we want to do is find the volume of revolution of the outer curve and then subtract off the volume of revolution from the inner curve. So the first thing to do is just say, hey, suppose I weren't worried about this region. Suppose I just wanted to find the volume of revolution that I get when I rotate f of x about the x-axis. Well, your characteristic rectangle would look like this. And we would get a cone when we revolve this around the x-axis. And what we want to recognize is that these are our dx slices, and our radii would just be the y-coordinates. So our radii in this case would just be f of x. And this is the curve above, so I'm going to call that the big radius. I'm going to let big radius equal f of x. So if I wanted to calculate the volume of revolution for f of x about the x-axis, I would do exactly what we've been doing. I would say, hey, it's going to be pi r squared, but I'm going to run my integral from a to b. I have a closed interval over which I'm interested in calculating the volume. It needs to be pi radius squared. My radius is just my function because up here I have ordered pairs f of x, so the height of the rectangle is the radius of revolution. So I square that, and then I have to multiply by the width, which is dx, and that gives me, that adds up all the volumes of those infinitely many disk or cylinders that are underneath this curve. And then what I want to recognize is that includes the volume underneath g of x, which I want to exclude here. So the idea is, well, then just rotate g of x about the x-axis. So these widths are still going to be dx's. I'm still going to be running from a to b, but now my radii of revolution will be given by the function g of x. So I just subtract off the extra volume. So I calculate the volume from a to b underneath the volume that I get when I rotate g of x around the x-axis. So g of x is the radius of rotation or revolution. So g of x squared pi r squared. There's the area of the circles of revolution times dx, the height or width of that rectangle that I'm revolving. So get the outer volume minus the inner volume to get the volume in between the two curves when you rotate it. So this is just subtracting off this inner piece. And then when you see this, you want to recognize that the bounds of integration are the same. The constants out front are the same. So we could combine this into a single integral. We could say take pi times the integral from a to b. The bounds of integration are the same. the constant factors out front, and we wind up with f squared of x, the larger radius squared, minus g squared of x, the inner radius squared, times the dx that shows up in both terms. And if you're representing the outer radius with a big R, then you can just replace f of x squared with big R of x squared. And if g of x, if you represent the inner radius with the little r, you replace the g with little r of x, saying, hey, get the volume of revolution controlled by the large radius, subtract off the volume of revolution controlled by the smaller radius, and that will give you the volume of the washer that you've swept out.